We're in Visual Studio, and what I'd like to do is take a relatively quick look at a binary tree implementation that is included with this module. Now I want to be clear, this is not a production quality binary tree implementation. This is a learning implementation. Some things are overly verbose. Some things aren't done the way they would be done in production, but they're done in a way that helps make them clearer for you to understand. So please keep that in mind when we're looking at the code. And if you're looking at using a binary tree in production, look to your platform and find out what's available. So we're starting with the binary tree node. Now remember from the slides that the tree is built up of nodes that contain data. This should be very similar to what we've seen with linked lists and stacks and queues. The node contains a value and a left child and a right child. We also have the ability to compare the node to other nodes. And that comparison is simply based off the value comparisons. Now let's look at our binary tree. So our binary tree is enumerable and the values we store are comparable. And that's really important because to actually do a binary search tree, every item you put into it has to be comparable to the values that are around it. So if we couldn't compare them, we'd be in trouble. So we have the head of the tree, that's the head node, and the count is the number of nodes in the tree. Count isn't really meaningful for the tree structure, but it's one of those kind of little helpers that we like to use. Let's start with add. Now add is pretty simple. It has two cases. If head is null, we just assign head to a new node. That's the case where the tree was empty. And if head's not null, recall that we go into a recursive algorithm where we call add to, providing the head node and the value. This is just like we saw in the slides. And just like in the slides, we decide, is it less than the current value or is it greater than or equal to the current value? And that's all you need to do. And go ahead and look at the code, compare it back to the slides to understand it, but it's all very straightforward. If it's less than the current value, we start head and left. If there's no left tree, we make it the left tree. If there is a left tree, we recursively call add. If we need to go to the right and there's no right tree, we can make it the right tree. Otherwise, we recursively call add. Now contains is going to call a helper function called find with parent. And the reason we're calling find with parent is so that when we get the value back, we also get the parent node back. And this is really important because remember that when we were doing remove, remove needs to know the parent of the node we're removing so that it can properly readjust the links. So instead of having contains operate differently than remove, and instead of reduplicating that code, I've just pulled out this helper method called find with parent, and contains just ignores the parent. And if the value is non-null when it returns, it contained the thing. So let's go look at find with parent because that's where the bulk of this is. Find with parent actually isn't that complex of a method. We start with setting current to be the head because we're going to start with the head of the tree. We're always going to do that when we're trying to find a node. And what we're going to do now is say while current does not equal null. And that's because this is not a recursive algorithm. We're not going to recursively call find with parent. We're going to iterate over the nodes. So let's do a value comparison to find out if we're greater than or less than. If the value is less than current, we need to go left. So we set parent to current and current to current.left, and then we'll loop again. If the value is greater than the current value, we're going to go right. So parent will be set to current, and current will be current.right. Otherwise, we have a match. And if it wasn't less than and it wasn't greater than, it must be equal, so we break and we return current. So all we're doing here is walking the tree and making a decision. If it's equal, I return it. If it's less than, I go left. If it's greater than, I go right. And when we're done, the value we return is the found node, and the out parameter parent will be set to the parent of the found node, or null if it was the head node that it found. So that's how contains ends up finding out if the value we're looking for was found. And now there's remove, and remove is where things get complex. Recall that there's 3 cases we need to concern ourselves with, and we're going to look at those somewhat briefly in order, and I would refer you back to the slides to understand these in more detail, because it really is a lot to cover in code, and the slides presented it in a more visual manner that might be easier to understand. So the first step in every case was to find the node that we're going to remove, and to find its parent. If current is null, that means we didn't find it. We'll return false because nothing was removed. If current is not null, well, then we found what we're going to remove. So we can go ahead and just decrement count right away. It doesn't matter if we do it now or later, but doing it now is fine. So the first case, the node we're removing has no right child. So the node we're removing's left child replaces the current. And that's what we're going to do in this block of code. If parent is null, that means that we are removing the root node. So all we need to do is promote the left child up to the root node. But if parent is not null, then what we're going to do here is figure out, are we updating the parent's left child link or the parent's right child link? Now this is a bit of information we lost in the find method. We know what the parent node is, but we don't know if we got to the child to the left or the right. So we're just going to figure that out again. If we got to it from the left, then the values are less than. If we got to it from the right, the value must be greater. And it just tells us which parent link we're updating. But no matter what one we're updating, we're setting it to the deleted node's left child. In the second case, the current's right child has no left child, so the current's right child replaces current. And again, we start by figuring out, are we removing the head node? And if we are, just promote the child. If we're not, again, we need to figure out which of the links, the parent's left or the parent's right, should we set to the right child. And finally, if the deleted node's right child has a left child, replace the deleted node with the deleted node's right child's leftmost child. It's a little bit complex, so here's what we're going to do. The leftmost child is the current node, which is the node we're deleting's right child's left child is our starting point. And the leftmost parent is the parent of the leftmost child. And we just keep looping, and we're saying, hey, while there's still a child to the left, keep going left, keep going left, keep going left, over and over again until we run out of nodes to the left. Then we start updating the subtrees. And this is that same kind of logic again, where if we're updating the head, then we just promote the leftmost child. Otherwise, we need to figure out if it's the left or the right of the parent that gets the leftmost child. And I understand I'm glossing over remove somewhat quickly, but that's because we spent so much time on it in the slides. If you have questions about it, look at the tests that ship with this course and spend some time running through them. Finally, we have the traversals. And recall that the traversals are all implemented as recursive algorithms. And what changes is in what order the processing versus the left and right walking occurs. So the way I've implemented the traversals is to take an action or a delegate that will get performed each time the node is processed. So in the pre-order case, if the node is not null, we perform the action, and then we go left, and then we go right. Remember, that's exactly what pre-order does. It's process the node, go left, go right. And what we're doing here is a recursive algorithm. It just loops around and around until we hit the null nodes, which is our terminators, and then we return. Post order is the same, only instead of doing action pre, we do post action. It's the same algorithm, we've just changed the ordering of the operations around. And you should be able to guess that in order then, if it's not action walk and not walk action, it must be walk action walk, or left process right. But I wanted to show an example that wasn't recursive as well, because as great as recursive algorithms are, they have problems and they have limitations. And if you have a tree that had 1,000,000 nodes, are you really going to call this recursively in a pathologically bad case potentially 1,000,000 times? You'd run out of call stack, you'd crash your application. We don't want to do that. And no production quality tree should do that. No production quality tree should use this recursive algorithm. So what I've implemented here is I've just taken the in-order traversal and I've made it non-recursive. And we make algorithms non-recursive using a stack. So what we're doing is we first say, is the head null? Is the list empty? If the list isn't empty, we have things to traverse. So we create our stack. And since it's non-recursive, we're only going to create one stack during the traversal. Our current node that we're on is the head node. And since we're removing recursion, we need to know whether or not we should be going left or right. Because remember, when you're doing a recursive call, you call walk to the left. And then that all returns. Then you go on to the next action, which is process the node. And then you call walk to the right, and that performs all the recursive actions and comes back. But in this case, we're in a while loop, and we need to know, did I already go to the left? Should I be going to the right? And what is the state that I'm in? And we use this as an indicator. We're saying, should I be going left next? And in order traversals, we start by going to the left, so it's true. So go left next is set to true. We're going to push the current node onto the stack. Now imagine we made a call. In .NET, when you make that call, what happens? Well, the stack frame gets allocated, and the values that you pass to that call go on the stack. So what did we do? We put it on the stack while our stack count is greater than 0. So this is while we haven't removed everything from the stack, or if this were a recursive call, while we haven't returned from every recursive call. If we're going left, well, let's start doing that. Let's start walking left and push everything on the stack to the left. Because remember, this is a walk left first, then process, then walk right. So we don't need to do this onesie-twosie. We can just say, hey, go to the left all the way. If there's 8 nodes we have to walk through, let's walk through all 8 of them, because that's what would happen. So we walk all the way to the left. We keep track of what the current node we're on is, and we push it back onto the tree. Once we've walked all the way to the left, we yield that value. That's that C# syntax to return that value as part of an enumerator. So when we walk all the way to the left, we're returning the value of the leftmost node. Now, what we're saying is, okay, we've processed the value, we've gone all the way to the left, so what do we need to do now? We need to go to the right. So we set current to be current.right if it's not null. And now that we've done that, we need to start going left again. Because remember, we just made a call to the right. And what's the first thing that right node should do? It should go left. Now, if current.right was null, what we're going to do is we're going to pop the value we just processed off the stack. And since we've already processed that value and gone left on that value, it's time to go right. So go left next is going to be false. So we're going to come back up to the top here. Is go left? Nope, we don't go left because it's false. We're going to return the value, which is the one we have processed the children of, but not itself yet. And now if it has a right node, we start processing it. Otherwise, we pop another value off the stack. And I know it's hard to visualize this, but debug through this a few times. Get comfortable with it and understand how the stack is being used to emulate recursion. And also think about why this is a good thing. Your stack can hold 1,000,000 items in it. And that's going to have memory constraints. And, there certainly are issues that might happen there, but you're not going to have the call stack problems that the runtime would have if you tried to make 1,000,000 recursive calls. So you've shifted the problem from a runtime call stack depth problem to a memory constraint problem. And that's one that people tend to be able to understand and handle a little more gracefully. I provided a get enumerator that simply returns the in-order traversal. Clear sets head to null and count to 0, and count simply returns count. So that's all at the end, things we've seen before and should understand.